It's my pleasure to introduce Dr. Wong. Dr. Wong is an assistant professor in the Department of Population Medicine at Harvard Medical School and Harvard Pilgrim Healthcare Institute. She received her master's in epidemiology from University of Ottawa and her PhD in epidemiology from McGill University. She also previously worked at the Institute for Clinical Evaluative Sciences in Ontario, Canada, conducting population-based studies using data from linked administrative healthcare databases. Her research focuses on generating evidence to inform the appropriate and safe use of marketed medications in real-world settings, particularly when they are used beyond their labeled indications in the absence of supporting data. So she is perfect for today's session. She has extensive experience working with large electronic healthcare databases, included administrative claims data and electronic health record data, where another major focus of her research is on leveraging machine learning to improve tasks like risk adjustment, computable phenotyping, imputed missing data, extracting information from more complex data types to enhance the utility of real-world data in pharmacoepi research. So it is my pleasure. Thank you, Dr. Wong, for joining, and I'll turn it over to you.
Well, thanks again for that introduction, and thanks for the opportunity to speak today. So as Jody mentioned, I'll be talking on the topic of applying machine learning in distributed networks that conduct activities in post-market surveillance, and focusing on opportunities, challenges, and considerations. So here are my disclosures. I received some support of my effort through my involvement on some method center projects in the Sentinel Innovation Center. But all views that are discussed in this presentation reflect my own perspective. So today's talk is going to be based on a paper that I published with my co-authors in a special issue of Drug Safety that was on the topic of the role of AI and machine learning in pharmacovigilance. So I want to take a moment to acknowledge my co-authors who are active investigators in the Sentinel system and the OHDSI networks. And so the nature of today's talk is, like the paper, going to be very much of a discussion style presentation. It's going to cover a broad range of topics, but at a very high level to paint a bird's eye view of how all of these different topics and activities all relate and interact with the use of machine learning in distributed networks. And as this paper was published in the spring of 2022, shortly before the release of ChatGPT, and as we all know, the explosion of large language models and generative AI, I think it's worth thinking about how these newer technologies might be able to accelerate our ability to address some of the challenges that we talk about today. And so that might be something interesting to hear from you in the Q&A afterwards. Okay, so here is an overview of the talk today. We're going to be starting with some key definitions to define what we mean by machine learning and distributed data networks. And then we're going to move on to talk about key activities that distributed data networks who conduct activities in post-market surveillance, what type of activities they do, and then how machine learning can be used to enhance these activities. Next, we'll talk about some practical data-related aspects of distributed networks and how they impact how distributed networks do their work. And these factors can help us understand the types of challenges that they face when performing machine learning as compared to in a single site setting. Then in the next section, we're going to consider 4 different scenarios of distributed networks, and these highlight how the practical factors that we consider impact the ability to apply machine learning. And these impacts lead to challenges. And there are different approaches that we'll discuss that can be used to address these challenges. And we'll look to some examples from efforts in the Sentinel system and OHDSI network that have been used to try and address these challenges. And then lastly, we'll close with some additional considerations and conclusions. Okay, so for definitions, I want to start off by defining what do we mean when in this talk when we talk about machine learning. So I always like this diagram. So this diagram on the left, on the y-axis on the left side, shows algorithms that generally they exist along a continuum from being fully human guided to fully machine guided, and the degree to which an algorithm can be considered an instance of machine learning really depends on how much of the algorithm's decision-making ability is determined by the machine's decisions rather than human input. So on this spectrum, you can see that human decision-making would fall at the bottom of the machine learning spectrum. And then above this, we have the regression analyses and models that we often use in epidemiology, where although the parameters are estimated by machines, still the specification of the inputs into the model are heavily dependent on human decision-making. And then above this are more flexible and data-adaptive algorithms like deep learning models, like convolutional neural networks and random forests. And so in this talk, we'll use the term machine learning to refer to these types of algorithms that sit higher up on the machine learning spectrum and have as much, if not more, input into the decision-making of the algorithm than human input. And so if you'll notice, this figure was published in 2018 in the pre-ChatGPT era. So if we were to update this figure to today, it might look something like this, where now at the top we have even larger deep learning models called like foundation models that have trillions, billions, or even trillions of parameters. And so another thing that this figure demonstrates is that the higher up that an algorithm sits on a machine learning algorithm, also in general, the more data is required to train these models. So one way to access larger and more diverse populations is to conduct multi-database studies. And there are many well-recognized benefits in pharmacoepidemiology about using multiple databases. So you can get more precise and generalizable findings. You can better study rare exposures and outcomes. You can better study heterogeneous treatment effects. And now we can say they offer more data that we can use for machine learning algorithms. So one way to conduct a multi-database study is to form a distributed data network. And so a key trait of a distributed data network is that its data partners do not pool their sources centrally. Rather, each data partner maintains full control over the physical storage and how their data is used. So for example, the data partners could choose to share de-identified data, their de-identified individual level study data with the coordinating center. Or they could choose only to share aggregated data, or they could choose to refrain entirely from participating in the study. So the main point is that the control of the data always rests with the data partner. So as I'm sure this map may be, or these logos may be familiar to many on this call, here are some examples of distributed networks that use observational health data to assess the effectiveness and safety of marketed medical products. So in North America, in Canada, we have C-nodes that responds to inquiries from Health Canada. And in the US, we have the Sentinel system and OHDSI that support FDA in post-market surveillance of drugs and biologics. In the US, we also have PCORNet and the Healthcare System Research Network. And as shown by the number of OHDSI logos on the map, you can see here that OHDSI is also an international network and collaborative. So they have data partners and sites across the globe. And so they also partner with, work closely with distributed networks in other countries like Eden in Europe and also Aspen in the Asian region. So for this talk, the examples that I'll be drawing from come from the Sentinel system and the OHDSI networks. Okay, so moving on to the next section, we'll talk about key activities of distributed data networks. So distributed data networks that focus on post-market surveillance, many of their activities could be mapped to one of four domains. So the first domain is computable phenotyping, which is the process of deriving computer executable algorithms to identify individuals with certain conditions or diseases or characteristics from measurable information in a database. And so these computable phenotypings help us construct the analytical data set and define the study cohort for a study or an activity that we're going to perform. So once the study data set has been created, then it's used to perform downstream activities in the distributed network. So these could include safety signal detection. And so these are activities that generate hypotheses about new or unsuspected adverse events that may be related to the use of a medical product, but they require further investigation to determine if it's a true causal effect. So then next, another activity that these networks perform is causal inference. So where these hypotheses are now more rigorously tested to determine the impact of medical products on health outcomes. And then these distributed networks also perform what I call forecasting activities, and these are to try and predict the risk of future health events occurring in individuals to help with tasks like early planning and prevention, or even for risk adjustment and analysis. So with all of these activities, the question is, how can machine learning help to enhance these activities that distributed data networks perform? So for computable phenotyping, one use of machine learning is to help select the inputs and learn how best to map the inputs to an individual's phenotyping status. So this is whether or not they have the phenotype. And this use is especially valuable given the growing amount of information that we'd like to use from electronic databases to help us craft phenotypes. And so these can help us select which ones to use and how to model them. And as we know, in electronic health databases, they contain both structured and unstructured data. And the amount of unstructured data is actually more than the structured data, and they contain very rich information. So there's interest to incorporate this information into phenotyping definitions. So this is where another use of machine learning can come in, which is for information extraction, to extract candidate inputs that have potentially relevant phenotypic information and to structure it so that it can be used in the phenotyping algorithm. So to show some examples of potential benefits of machine learning in crafting a computable phenotyping algorithm, showing some findings here from a recent Sentinel Innovation Center project where it was developing a computable phenotyping for anaphylaxis, which is a life-threatening allergic reaction that's typically hard to identify from structured data. So this, in this study, the considerations for the phenotyping were both structured data as well as information extracted from unstructured data using NLP, and as well a comparison of how machine learning and traditional regression methods perform. And so as you can see, the best phenotyping model was the one that used machine learning as well as features that were extracted both from structured and unstructured data. So in signal detection activities, first it might be helpful to consider what types of methods are usually used to conduct signal detection. So in this table comes from a recent systematic review that was showing different methods that are used for signal detection from routinely collected healthcare data. So from the table, you can see that among the most common approaches are ones that adapt disproportionality analysis methods to signal to longitudinal or routinely collected healthcare data, as well as studies that employ traditional epidemiological designs. And just a note that this table is not mutually exclusive. So for example, you can use the tree-based scan statistic with the new user cohort, which has been done before. So the uses for machine learning here in signal detection, first of all, is known or has been used for one type of disproportionality metric called the information component. So this has been estimated using a Bayesian confidence propagation neural network. And originally it was designed or used with spontaneous reporting data, but has been adapted more recently for use on routinely collected health data. Machine learning can also be used in studies that employ traditional epidemiological designs to help construct the propensity score to reduce confounding. And the propensity score is a model that estimates the risk of exposure conditional on covariates. And there's also room in signal detection for creativity and other innovation designs for how to identify drug outcome pairs that may be signals. So I've cited here a paper that was published by Jenna, who is a member of OHDSI, where she proposed a framework using a supervised machine learning model, in this case a random forest, that was able to identify drug outcome pairs that represented adverse drug events using a vector of features that represented effect estimates from cohort studies that were constructed to represent different Bradford Hill causality considerations. And so finally, machine learning can also be used to help extract mentions of adverse drug events from clinical text. So that can help identify more outcomes of interest to scan across in the analysis. So in causal inference, machine learning can be used for high dimensional confounding adjustment. And so one common use is to estimate what we call nuisance functions. So these really are functions like the propensity score and the outcome model that are not of primary interest, but they are used as inputs to the causal estimator. And so machine learning has been commonly used, especially in doubly robust methods like targeted maximum likelihood estimation. But machine learning can also be used to help prioritize or even reduce the dimensionality of the covariates in the analysis. Another use of machine learning in causal inference can be to extract candidate covariates from unstructured data. Certain covariates of interest may not be well captured in structured data, so by extracting them from unstructured data, this could help improve confounding control. And finally, a more recent use of machine learning that has captured attention is the use of machine learning for counterfactual prediction. And this is when we predict potential outcomes for individuals under different treatments to help with clinical decision making. And so finally, for the fourth activity, forecasting, the benefits of machine learning in this type of activity is actually very similar to those for computable phenotyping, which we discussed earlier. And so this is because these tasks follow a similar process when they're deriving their machine learning models. So in computable phenotyping, where we have an index date and we look for predictors and we use machine learning to predict if the individual has the condition on the index date. In phenotyping, it's the same setup for the predictors, but instead we are predicting the probability of an event developing at some point in the future. So in these types of, we call them prognostic prediction activities, the use of machine learning can be used to, again, select which might be the best predictors for use in the prognostic model and best learn how to map it to the prognosis. And it can also be used for information extraction, to extract information that might be valuable prognostic markers of health outcomes and to use those as features in the prognostic model. Okay, so hopefully I've convinced you all that there are many different uses that we can, that machine learning can be used for in distributed data networks. And so now we'll switch gears and talk about practical aspects of how distributed data networks work and do their activities, which are important for understanding the challenges that we'll discuss in the next section. So the first data-related factor to consider is what modality of source data that the distributed data network uses. And so the possibilities for a distributed network could range from using solely structured data in their activities to using solely unstructured data. And traditionally, distributed networks have primarily used structured data in their activities, but given the rich information that we know is stored in unstructured data, there has been an interest to move more towards incorporating more unstructured data into their activity. The second factor is the degree of standardization of the data that the network uses. So networks can exist from the possibilities of having on one range all of the data that is used in a common data model or CDM. And so common data model is basically where the data from each site exists in a common structure and a common format. And then on the other end of the spectrum, we could have no common data model at all, where all data partners keep their information in the native format, and instead they might apply a common protocol. So most distributed networks now use a common data model, and ones that in the past that may have used a common protocol approach. So for example, C nodes started out using the common protocol approach, but over time, these networks have moved towards adopting a common data model because of the benefits that this standardization has for increasing the efficiency of activities in going forward as more analyses are conducted within the network. And the last factor is the granularity of the shared data. So again, there's a range of possibilities. So distributed networks could share de-identified individual level data with the coordinating center, or they could share summary level data. And just to specify, these individual level data sets would be like not the entire database that the site has. It's the crafted data set for the analysis. So in this case, where a network sits on a spectrum is determined by factors like maybe the strength of their collaborative relationships at the time that they formed. And it definitely can also be affected by legal and administrative considerations. So among all of the distributed networks that we have discussed so far, there you can see that most of them sit on the end of sharing summary level data, but there are some networks that do share de-identified individual level data. So these are the CoreNet and HCSRN. Okay, so now that we have identified the different data-related factors and the different possibilities that a network could have with regard to each of these factors, we're going to consider 4 scenarios of a distributed data network and the challenges that a network could face if it was in that scenario. So the first scenario is what I will call the base case scenario. So this is where the network uses only structured data in all of its activities. When it's fitting a machine learning model, all of the inputs for the model come from the common data model. And the granularity of the shared data with the coordinating center is individual level data for all sites. So in this case, it is logistically the most straightforward to apply machine learning. This is because the structured data facilitates the creation of the common data model. It's relatively easier to map the structured data to a common data model when the underlying data is structured. And then to create the analytical data set for the machine learning models, if everything comes from the common data model, then it can be facilitated with the use of common programs and code. Even though this is logistically straightforward and the machine learning model could be fit with the same amount of flexibility in a single site setting, it may not always be the most scientifically valid approach. So this is because whenever you're working in a distributed data network, you need to think about factors like heterogeneity in the data across sites that could result from things like differences in practice patterns or coding practices between the sites. And these could degrade the generalizability of the machine learning model developed in the distributed network, even if you could technically analyze them all as a centralized database. And so underlying heterogeneity is tricky to deal with. And so it can even exist in seemingly similar sites. This is what we found in a Sentinel Innovation Center project that we recently completed. This was led by Dr. Shushi from University of Michigan. And so we had defined a cohort of adults with any diabetes, and they came from two sites within the Kaiser Health Network. And from the table on the left, you can see that overall, from their general clinical and demographic characteristics, they seem quite, comparable. Nothing strikes out as much different. And even if looking at the codes within one condition of cataract, which is a condition that is more common in individuals with diabetes, you can see that the overall frequency looks like it's about the same. But if you drill down deeper into the specific codes under this cataract group, you can see differences that start to emerge. So, for example, we found that at Kaiser Northwest, there was greater use of unspecified codes. And at Kaiser Washington, there was greater use of specific codes. And when we looked further into these differences, we found it was due to differences in the way that the two sites billed for eye-related services. So this example is to show that heterogeneity is something that is always important to consider in a distributed data network. And the consequences, for example, if a machine learning model were to be trained on codes at this level of granularity, then the models might not generalize well between the sites because of this issue. So what can we do to reduce heterogeneity? Well, one approach is that we could fit site-specific models. However, this reduces the amount of data that's available to fit the model. And so a second approach could be to instead harmonize the input data. And when I say harmonize, I mean take the input codes from one site and map them to the closest value in the corresponding or the reference site. So this is what we did in the study. We used an unsupervised learning approach where we fit or we trained code embeddings in each of the Kaiser sites, and then we used these site-specific code embeddings to create data-driven mapping of the codes, and the direction was from KP Washington to KP Northwest. And so, as you can see, I'm just giving one example here, that even just using a machine that could not actually read the definitions on these codes, that this type of unsupervised mapping was able to logically map more specific codes from KP Washington to the unspecified codes in KP Northwest. And so, as further evidence or metrics of how the heterogeneity from this mapping is reduced, we found that before harmonization, if you just use the cataract to predict which individual, which system an individual is from, you could get an AUC of 7.72. So showing that there's some heterogeneity in the data that's distinguishing the patients from the different sites. But after harmonizing, the AUC of the model decreased, so that the machine learning model here was less able to distinguish between which system the patient was from. So this discussion all is to demonstrate the importance of heterogeneity in distributed networks, but also the different ways that we could try and deal with this heterogeneity. All right, so moving on to the second scenario. So we'll now consider a second scenario where everything from the base case remains the same, except for that there exist some inputs that we desire for the model, the machine learning model, that are not found in the common data model. So they exist outside of the CDM in the data partner's native format. And if we take this even a step further, an extension on scenario 2 would be a situation where we have now both structured and unstructured data that we'd like to use in the model, but some of these data sit outside the common data model. And these are important scenarios to consider because they create challenges for sites and the networks to create a common set of features with a common format that they can use for their machine learning activities. So yes, as I mentioned, challenges for feature engineering. So just to demonstrate how common or how prevalent this problem actually is for distributed networks, this is a table from a paper that Judy Morrow from our group here at the Sentinel Operating Center published last year. And this was this table here is showing a summary of the different reasons why drug safety concerns could not be evaluated in the FDA's Active Risk Identification and Analysis System, or ARIA. So from the table, it shows that unavailable structured and unstructured clinical data in the Sentinel Common Data Model were among the top reasons that drug safety concerns could not be evaluated. So what can we do when information that we want is outside of the CDM? Well, one approach is to standardize the unstandardized information. And so this sounds very logical, but in practice, we know that this requires a lot of time and resources that have to be invested upfront to do this. So as a result, distributed networks consider carefully what they do when they do it. Some considerations they think about are how, for example, how easy can it be for the information to be added? How frequently will the information be used? And this can be sort of a proxy for how valuable that information is to the activities of the network. Or how urgently is the information required? So, for example, in responding to a public health crisis like COVID. So to give some examples of what types of additions have been added to the Sentinel Common Data Model over time, in this flow chart on the right, you can see in 2020, there was addition of laboratory diagnostic test results for COVID-19 to the laboratory table. In 2020, there was a patient-reported measures table to the CDM, and that would be very useful for inputs to machine learning models and also for epidemiological analyses. And most recently, in the latest upgrade to the Sentinel Common Data Model, there was the addition of the feature engineering table. And this is a table that will support extraction and standardization of information from unstructured text into the EHRs. And so given the significant challenges that we know come along with trying to extract and standardize information from free text, I think these activities highlight the value of these data for enhancing the activities of distributed networks, including those that will involve machine learning. And so Sentinel system is not alone in creating space in the CDM for NLP or information extracted from unstructured text. The OMOP Common Data Model, which is what is used by OHDSI, has also had a table for notes and information extracted from unstructured data. And so I think since 2017, these two tables, where the note table stores the original text and the note NLP table stores the outputs from the pipelines that have been applied to extract the text, those are also components of the OMOP CDM. But sometimes it might not be feasible to try and standardize the information. So another option to still proceed with the machine learning analysis is to perhaps do a site-specific analysis and use a common protocol. And so in some cases, this approach might be preferred. For example, there may be some sites that have some types of information that other sites don't have. And so by allowing each site to do their own protocol, or according to a common protocol, but allowing them to each do their site-specific analysis, you could compare the benefits to the results or the changes in the results when desired information is added at certain sites that have that information. Also, this may be preferred when the value of the desired information that will be used in the model is uncertain. And this might happen often when trying to come up with a large candidate list of features to include in a machine learning model and not knowing which ones will be the most predictive or valuable. Okay, so on to finally the last scenario. So this scenario, we move back to the base case scenario for the source data and the degree of standardization of the data. just for illustrative purposes. And now we focus on the granularity of the shared data. So now we're in a scenario where the distributed data network can only share summary level data, which, as we mentioned earlier, is the case for a lot of distributed networks. And this scenario creates challenges because it impacts how machine learning models can actually be trained by the network. And this is especially challenging for models like deep learning models that use an iterative process like gradient descent to train their models. So how can we train machine learning models with only summary level data? Well, one approach is to collaboratively train a global model using an approach called federated learning. So with federated learning, briefly to describe, there's an aggregation server that coordinates all of the updates to the global model. So it starts with the global model and distributes this global model to each of the sites in the network. Then each of the sites in the network use their local data to train, to further train the global model. And then they take the model that they have trained and send that local model back to the server, but only the model and not their training data. Then the aggregation server takes these local models and then uses some approach. So simplest could be, for example, just averaging the parameters or the weights from the model, and then updates the global model. And then these updates to the global model represent the new global model, which is then repassed to the sites in the network. And so this process repeats until the global model reaches some sort of predefined evaluation criteria. So, so with this approach, there are obviously some advantages. So by using data from multiple sites, we can train more robust and generalizable models. And I wanted to show a fairly recently published study that was conducted by OHDSI researchers in the OHDSI network, and they used federated learning to train a global model to predict bipolar transition in patients with depression. And so what they found was that the federated model was able to achieve a higher AUC than all the local models in the test sets among the sites that were used to train a federated model. And then also when the models were tested in a new external database, they found that the federated model also performed better than local models. So this is supporting the advantage of using federated learning to create generalizable models. However, there are some obviously disadvantages with this approach. So one challenge is that it also comes with concerns about privacy leakage whenever the gradients are shared during the model update. There is always risk of sharing private information about the data at the data partner site. Another disadvantage is the challenges that come along with trying to coordinate and implement federated learning models. So it may have lots of hardware and infrastructure requirements, and also the number of communication costs required going back and forth between the sites and the aggregation server. And finally, the global model may not converge well or perform well if the data across the sites are too heterogeneous. So as an alternative, if federated learning is not an option, of course, distributed data networks can still train custom models at each site, and they can train these models independently. And so different from training, for example, the global model in the federated learning approach. So some advantages of this is that when you train machine learning models within a distributed network, these models can be easily validated in other sites. This is because the use of standardized data and programs facilitates the ability to take a model and then quickly evaluate it on another site in the network. Another advantage is that you don't necessarily have to be restricted to using the same inputs as the other sites do for the machine learning model in the network. And finally, another approach is that the transportability of local models can also be improved using simpler federated learning approaches. And so I've linked a paper down below that was published by Jenna again from OHDSI, where she showed that you could use machine learning techniques, so specifically ensemble techniques, which combine predictions across multiple machine learning models. And this approach could be used to try and improve the performance of externally trained models when applying it on a new data set within a distributed data network. And of course, the disadvantage of this approach is that you still don't harness the full potential to train a single machine learning model. So I want to end with some additional considerations and conclusions. So for all of the challenges that we discussed in the previous section, we discussed various approaches that you could take to address these challenges. But really, there is no one right or best approach all the time when you're using machine learning models for different tasks. But really, it comes down to more of a balancing act between three constraints. So you want to, obviously, the goal is you would want to optimize performance of the machine learning model. But this also comes at a price sometimes. For example, if you want to extract more features from unstructured data, then it will become more costly to do this. And then also another constraint is on the privacy that can be maintained by the sites. And so certain approaches that you can consider will they represent a trade-off between these different factors. And so the best approach for a situation is the one that achieves the best trade-off between all three of these factors when considering which approach to use. However, this trade-off can be further influenced by other factors like the degree of heterogeneity across the site, also the sample size that's available at each site, and also, importantly, what is the purpose of the machine learning model? For certain uses, for example, a propensity score model, it may not make sense to try and train a global model, whereas for training a forecasting model or a computable phenotyping model, perhaps at a small site, it may be more attractive to try and collaboratively train a model across the site. So all that to say is that really the choice of approach requires careful consideration of many factors that would influenced by the situation that the machine learning model is being used for. And so lastly, the use of machine learning and distributed networks also presents opportunities to address three issues that often plague the use of machine learning in single database settings. And so the first issue is related to evaluating generalizability. So often in single database settings, external validation of models doesn't happen very often, or it may take years to happen, whereas in distributed data networks, groups within OHDSI and Sentinel have shown that you can do this quickly and easily in this setting. Another second issue that distributed data networks are good for addressing is transparency of machine learning models. So in a single database setting, there may often be less reasons or impetus to document the finer details of a modeling approach, whereas in a distributed data network, the high transparency that comes along with trying to replicate the process across data partners may more naturally lend itself to a more transparent method when training machine learning models. And finally, interpretability of models. In single database settings, there may be less reasons to look into why a model predicts a certain way. This isn't to say it wouldn't happen, but perhaps there may be less reasons to prompt why this would happen. But in a distributed data network where every site is comparing how a model performed to another site, there may be more reasons to try and look and explain discrepancies that are being noticed across sites, and to be able to look more closely into the model and to what is driving those differences. So in conclusion, I wanted to close with what I think are my takeaway points. I know we covered a lot of ground in this talk. So first, we saw that there are many opportunities that exist for using machine learning to enhance the activities of distributed data networks that perform post-market medical product surveillance. However, in distributed data networks, the diverse and siloed storage of the data from partners creates unique challenges for applying machine learning. However, there are various approaches that can be considered to address these challenges, but the best approach requires considering what the situation for the exact use case of the machine learning model, as well as other factors surrounding the use of the model. As well, the rapid rise of large language models and generative AI in the past few years obviously has been very impressive with the capabilities that they've been able to perform or that they've been able to achieve. So these things may help accelerate the ability of distributed networks to address some of their current challenges. So for example, incorporating information from unstructured data into the common data model. But they may also raise new challenges and considerations. So my last point is to say that from the ongoing work and all the efforts that networks like the Sentinel system and OHDSI are making to harmonize both the structured and unstructured data and develop standardized processes and tools, I think it's clear that machine learning will continue to play an important role in advancing the capabilities of distributed data networks for post-market surveillance in the years to come. And so with that, I will end my presentation, and I'd be happy to take any questions or hear any thoughts that you might have on today's talk.
Thank you, Jenna, for that wonderful presentation. You've given us lots to think about and plenty of considerations. So we do have some questions here in the chat. I'm just going to go through and feel free. Eric, well, this one's from Eric. There are dozens of different cataract codes. I'm pretty sure that a machine learning model could predict ophthalmologists from the code that they use. But on more serious note, even the ICD-10 codes from a hierarchy snowbed code is better. How does the unsupervised learning compare to using the hierarchical information? Eric, you should have the ability to come off mute as well, if you want to elaborate more on that.
I would welcome if Eric has any additional thoughts to add. So if I understand correctly, I think he's asking, how does the unsupervised model compare if this is like a human derived mapping, or is that what he meant?
Just realized that was one. Says, how does the unsupervised learning compare to the hierarchical information? I think I guess maybe the human version, right? Compared to what you described here. Eric, if you have any additional information that you want to add there, please let us know. Otherwise, we can circle back to that.
Sorry about that. I'm not sure I quite understood the question.
And then we have another question from Adam Taylor. It says, what do you think the limitations and risks of this type of approach are? This is in reference to data harmonization and how you can train the models. And another thing that's mentioned here, it says, how do you mitigate the risk and limitations? So I think you touched on this a little bit, but
Is there, I'm sorry, I'm not quite sure I caught all of that question. Is there a way I can see, was it typed into a chat box or?
yes, so it should be in the Q&A. I believe
Okay.
you should
Yeah,
have
this
access
is
to
very
that.
helpful. Sorry, I'll look at it now. Okay. Um, Data harmonization. Okay, so what do you think the limitations and risks? Okay, so one limitation I think is that definitely with that approach of harmonization is that there's not always a one-to-one mapping. So in the graph that I showed, there's a lot of like tuning parameters in the analysis. So you have to choose a threshold on which you want to choose will be the closest code. And so you can have one-to-one mapping. You can also have one-to-many mappings. And you can, in that project, we actually limited the scope of codes from one site. So we actually limited to the fee codes within the cataract group from one site to map to the fee codes from the other site. I think if you blew up the whole analysis and allowed every single code to map to every other single code in the other site, you could end up with a lot of mappings. And so I think just being maybe putting certain parameters around the mapping can help you better understand what was being mapped to. So for example, in that project, we also limited it to the same type of patients. So patients with diabetes and adults over the same age, so that we could control for at least some of like underlying clinical heterogeneity that we would expect. And then beyond that, then we would suspect that maybe that would be differences in coding patterns and practice patterns rather than patients. Hopefully that was.
It does, thank you. Yeah, and I think just to build on Eric's comment as well, being able to map back to some sort of standard reference model as well can also try and minimize any of those risks, whereby you've got a standardized format, you can go in and manually check those things too. But yeah, no, that's great, thank you. And
Actually, I think if I understood that correctly, when you said like the manually mapping, do you mean like, so for example, in that project, what was nice is the codes with the eyes, it made a lot of sense because you would expect left eye matches to unspecified eye and right eye would also match that. In another clinical scenario, it may be less obvious that, two codes are the same. But I think having the labels on the ICD codes definitely helps make sense of the mappings to see if it is logical.
yeah, and then I guess if you map to a common reference model where you've got disparate labels or codes from different sites, then at least that gives you the centralized point for standardization to feed into any downstream models that you want to train.
Great point. Thank you.
Thanks.
We have another question from Patrick. So it says, okay, so first off, Patrick says, tremendous talk. Thank you. Very clear, very comprehensive. And he was wondering if you could share your opinion about the use of common phenotypes as features for machine learning algorithm as some bridge beyond using the common data model and individual codes concepts within there in that phenotypes involve algorithms that can contain temporal logic and more comprehensive code lists for any given clinical entity. With that, do you think that we should be testing machine learning algorithms using features that are phenotypes only versus concepts only versus phenotypes plus concepts?
This is a great question, Patrick, and this is related, I think, to some work that Patrick and Jenna and I and a few others in OHDSI have tried this approach, whereas can you replace individual like code level features with higher conceptual features like common phenotypes that describe more of a general condition rather than a specific, that's probably not clear, but a more yeah, a concept rather than a code. So you could have multiple different types of codes linking to a phenotype. So I think the main, I think the benefit of that is that it may help guard against some heterogeneity in the coding across sites. So if you create a bucket that is broader, but still makes, still is able to distinctly classify between different clinical conditions, I think that is useful because it is, it's sort of going from a ground up approach for defining the phenotype rather than looking specifically at the level of the individual code. I hope that description made sense, and I hope that that I understood that comment correctly, but I think that's what he was getting at.
So we have one more here from Mark. It says, in your introductory review, you mentioned using machine learning for covariate dimension reduction. Could you give an example of successes or failures here?
Sure. Thanks, Mark. That's a great question.
Mark,
So actually a colleague of mine, Yannick Weber-Powell, he published a paper where he used a deep learning model called autoencoders. And so he used that as an alternative for the high dimensional propensity score method as a way of taking a high number of covariates and reducing it down to a small dimension space and using that in the model. And he found that it performed comparably to other, I guess, less complex methods like lasso to choose covariates. So to me, that would be an example of, well, it performed just as well. It didn't perform better, but so it's not a failure. I think it shows that it's an alternative approach that could be considered.
And Mark, you should have the opportunity to speak or come on video if you like. I know you had one additional question. Do you?
Yeah, that's okay. I had so many windows up. Jenna, thank you very much for that answer.
Oh, okay.
Yeah. The other question I had up there was related to the mapping of the billing codes, which you've already addressed, and related the idea of how does the unsupervised learning compare to using some sort of vocabulary and picking things at a higher level. But we are up on time, so I just wanted to take a moment to congratulate you on a fantastic and informative talk. Thank you.
Oh, great. Thank you so much for the opportunity.
I know there are a few questions in the chat that we were unable to get to. I will send those over to Jenna and we'll get you some answers as soon as possible. Thank you everyone for joining. Thank you, Jenna, for this wonderful presentation again. And all slides and recordings will be posted on our OHDSI website. Thanks everyone. Bye.